Delaware Tech, Chemistry 100, Chemistry 110, Neutralizations and Titrations. So a neutralization reaction is a reaction where you're adding exactly the same amount of base in terms of the moles of the hydroxide as you are to the amount of moles of acid in terms of the moles of the protons that the acid produces. And when those two equal each other, you have neutralized your reaction. You've neutralized the acid with the base, you've neutralized the base with the acid. And when you're using hydroxy bases, we always will end up with a salt of some type of ionic compound, and the water is formed from the addition of a proton, an H+, plus a hydroxide, an OH-, which end up forming a covalent bond between these two ions. And this is very favorable because it releases a lot of heat. So, when this is done drop-wise, in other words, you're taking some acid in a beaker or a flask, as shown here, and you've got your base in a container above it. This is called a pipette, or this is called a burette, and this burette holds a certain amount of base, and it has a stopcock which you can turn and allow one drop at a time to come out, and you watch it drop by drop until your acid is neutralized, and you stop exactly at the moment that it's neutralized, and then you measure how much of the base that you used, and you know the concentration of the base, and you can calculate what the concentration of your unknown acid is. Now, if you do this dropwise, if you do a neutralization dropwise, we call this a titration. So examples of the chemistry of what you're using would be starting with an acid and adding a base, or starting with a base and adding an acid. You could do the exact same thing, just switching the two in the flask and the burette. So in my first example here, I have nitric acid, HNO3, reacts with potassium hydroxide, KOH. And in this case, we're going to get, in all of these cases, since we're dealing with hydroxy bases, we're always going to get a double replacement reaction where we're going to produce some kind of ionic salt and water. So you see we've got a proton derived from the acid and an OH derived from the potassium hydroxide. They'll form water, and the remaining two ions will form a salt. And in this case, the salt is potassium nitrate, what used to be known as saltpeter. This is the active ingredient in gunpowder. About 75% of gunpowder is potassium nitrate. You can always look up what the rest is. I'm not going to discuss it right now. But the other product here is water. And I've written it as HOH to remind you that the H2O is actually formed from an H ion, an H+ ion, and an OH- ion. The second example we have is hydrochloric acid with barium hydroxide. Now, barium hydroxide has two hydroxide groups in it, but the barium will find the chlorine, the chloride resulting from the hydrochloric acid, and form barium chloride, and water will be formed. Now, notice that it's not balanced as it is, so now I've added the 2's here to balance it, and you see we now have 2 protons added to 2 hydroxides to make 2 waters, and then the remaining barium will mix with the 2 chlorides to form our salt. So everything is now balanced. If we look at the next one, sulfuric acid, this has 2 protons, and strontium hydroxide, which has 2 hydroxides. And since it's a 2 to 2, we don't need to balance it, and we're going to get strontium sulfate as our salt and 2 waters as a result of the 2 protons reacting with the 2 hydroxides. Another one is sulfuric acid, but now with sodium hydroxide, which only has 1 hydroxide. So you can guess ahead of time that we're going to need 2 sodium hydroxides to provide our 2 hydroxides for our 2 protons to make our 2 waters. And the last reaction is phosphoric acid, which is a triprotic acid, 3 protons, with barium hydroxide, which is a dihydroxy base. So we've got 3 protons here, and we've got 2 hydroxys here. Well, we're still going to make our salt, and if you actually balance the barium +2 ion with your phosphate -3 ion, and did your crisscross simplify to figure out what your final formula is, you'll see that you end up with 3 baryons in your salt and 2 phosphate groups in your salt. But in fact, you can figure that out even before you do the barium phosphate determination of the formula by noticing I have 3 protons here and 2 hydroxides, so I need 3 of the 2 and 2 of the 3. That would be a total of 6 waters that are formed in this reaction. And again, these are all double replacements because in each case, the cations, which are the positive charges in the bases, and the protons in the acids switch places, and the anions switch places. The anions would be the hydroxide in the bases and whatever is left in the acid. So in the case of nitric acid, it's nitrate, chloride and hydrochloric acid, sulfate and sulfuric acid, and phosphate in phosphoric acid. And that is how you determine your products. So, as I said before, a titration is just a drop-wise neutralization. You do it drop by drop, and you have to add exactly the same number of moles of protons from the acid as you do hydroxides from the base. And remember, some acids could have 2 protons, and some bases could have 2 hydroxides. Some acids could have 3 protons. So you have to be aware of that. But you calculate how many moles total from the acid, and that has to be exactly equal to the number of moles of the hydroxide from the base. So if you know the concentration of the hydroxide you're adding, that is the concentration of this material in the burette, and the volume that you ended up adding, because maybe you started up here and you ended up down here, and you look and that's your volume of your base that you used up. Whoops, sorry. Volume of the base you used up, and you already know the concentration of your base. Well, you know how much volume of your acid you have, but you have no idea what the concentration of the acid is. So you would do this kind of experiment if you don't know what the acid concentration is, or you could flip it around if you didn't know what the base concentration is, and you already have a standardized solution of acid. So either way will work. As long as you know 3 of these 4 things, you can solve for the 4th one. Well, how do we do that? Well, we know the volume of both, we know the concentration of the hydroxide, and we're doing this drop by drop until they're exactly equal, until the number of moles of protons exactly equals the number of moles of hydroxide. Well, what are those 2 values equal to? Well, the number of moles of protons are going to be equal to the moles of acid you have times how many acid groups are on that acid. So, for instance, for HCl, this number would just be 1, but for sulfuric acid, this number would be 2. And for phosphoric acid, this number would be 3. So you just look at how many protons the acid has, that's this number. And the base has the same sort of function in the formula. To figure out the number of moles of hydroxide you have, well, you take the number of moles of your whole base, and then you have to multiply it by how many hydroxides are actually on it. So if it's sodium hydroxide or potassium hydroxide, there's only 1 hydroxy per formula unit. Whereas if you were using, say, calcium hydroxide or one of the other alkaline earth metals, it has 2 hydroxides, so you'd put 2 in this number here. And then you just use the concentration of the calcium hydroxide or the concentration of the sodium hydroxide over here. So that's your concentration of base, and this is how many bases per base you have, how many hydroxides per base. Whereas this is your concentration of acid, and this is how many acid groups per acid you have. So you're really just calculating how many moles. Well, how do you get the number of moles of your acid if you don't know how many moles of acid or how many moles of base? Well, those can be calculated if you know the volume and the concentration of the overall compound. Because if you remember from calculating concentrations, concentration is defined as the number of moles, this is if it's in molar, by the way, we only use molar for this, the number of moles divided by the volume in liters. It's moles per liter. That's the unit. So if I rearrange this equation, the number of moles, which we abbreviate as N, is just equal to the volume times the concentration. So volume times concentration is the number of moles of acid, and then we just correct that for how many moles of, how many protons are actually on each acid. So if it's 1, we don't change it at all. If it's 2, we have to double our acid concentration to get our proton concentration. And likewise, with the base, we're multiplying volume of the base times the concentration of the base. That gives us how many moles of our whole base formula. And then if each base has 2 hydroxides, we multiply it by 2. If it only has 1, we multiply it by 1. And nothing changes. So here's your formula, and you have 6 different variables here. If you know what the compounds are you're working with, well, you know how many protons are on each acid, you know how many hydroxys are on each base. You can measure your volume of your acid, you can measure the volume of the base that you added, and hopefully you know the concentration of either the acid or the base to start with, and then you can calculate the other. But it doesn't matter which of these 6 you're missing, as long as you have the other 5, you can easily calculate what the 6th variable is in this by using this equation. So let's look at it. Let's look at some problems. Remember, everything happens in moles, so let's do some equations with just moles already calculated for you. You don't have to worry about multiplying volume times concentration. How many moles of nitric acid, HNO3, are needed to neutralize 0.86 moles of potassium hydroxide? Well, we know that 0.86 moles of potassium hydroxide, we know that potassium hydroxide only has 1 OH on it. So when we put this in water, we're going to get exactly 8.6 moles of hydroxide. It's going to be a 1 for 1. Well, we also know that a neutralization means that this number of hydroxides, this number of moles of hydroxide, has to be exactly equal to the number of moles of protons. So it's also 0.86 moles. And we also see that there's exactly 1 proton for every nitric acid, so these 2 concentrations will be the same, and therefore the number of moles of protons will be exactly equal to the number of moles of our nitric acid. That's, again, it's a 1 for 1 relationship between the number of moles of the acid and the number of moles of the protons being released from that acid. So this is a very simple equation. You can actually do this in your head and realize that they have to be exactly the same because they both release 1 of their ions, 1 proton from each acid, 1 hydroxide from each base. If we have 0.86 moles of base, we have 0.86 moles of hydroxide, and therefore we need 0.86 moles of acid from 0.86 moles of nitric acid. The next problem, how many moles of HCl, hydrochloric acid, are needed to neutralize 3.5 moles of strontium hydroxide? Well, strontium hydroxide has 2 hydroxides for each strontium hydroxide. So if I have 3.5 moles of the compound, well then I must have 3.5 times 2 moles of my hydroxide, because I have twice as many hydroxides. Every one of these will produce 2 hydroxides. So I really end up having 7 moles of hydroxide that I need to neutralize from this compound. That means I absolutely need 7 moles of protons from my acid, and since this is a strong acid and this is a strong base, they'll be quantitative. So that means if I need 7 moles of protons, well then I can get that from exactly 7 moles of HCl, of hydrochloric acid. And that's how you solve that. But what if we have, so what if we have something more complicated? If it requires 45 mils of 1.0 molar NaOH to neutralize 57 mils of hydrochloric acid, what is the concentration of hydrochloric acid? Okay, well now we have a problem where we actually have to determine the moles. We're not just given the value of moles. So we know from our equation that the number of moles of acid times how many protons it actually has is the number of moles of our proton. And that has to absolutely be equal to the number of moles of our hydroxide. And this is the number of moles of our base. We multiply that by how many hydroxides for each base. That will be the number of moles of hydroxide. And we know those two have to be equal. So if we multiply these three together, we should get the product of these three values. So that's pretty straightforward. Now the beauty of this is, if you know any of these, and what are we looking for here? We're looking for the concentration of acid. We're looking for this variable here. Well, we can just divide both sides by the number of protons per acid and the volume of the acid, which we know. And we can do that over here, and those will just cancel, of course. And we can do that over here and have the number of protons per acid and the volume of acid. Sorry, horrible penmanship. Let's fix that, acid. And that will be our new equation for our concentration of acid. So literally, you're going to take all the base numbers and multiply them together and divide by the two acid numbers that you know, and you'll get the third acid number in the process. So let's do that. We have the acid is equal to the number of hydroxides per base times the volume of the base times the concentration of the base, and then we divide that by the number of acid groups per acid, the number of protons per acid, times the volume of acid. Now we have all these values. We know that there's one hydroxide per sodium hydroxide, and there's one proton per acid, so each of those are ones. We know our volumes are 45 mils of base and 57 mils of acid, so we put those in. And you notice we don't need to convert these to liters because the mils, in this case the milliliters, will cancel each other. So as long as the two volumes are identical, as long as the two volume units are identical, it doesn't matter what units you use here because they're going to cancel. However, your remaining unit has to be in molar for your answer to be in molar. And when you go through the math on this, you find your answer is 0.789. We round to two significant figures because you'll notice all the numbers in our problem have two sig figs. And our answer is 0.79 molar HCl. Now, does that make sense? Well, we started with 45 mils of a 1 molar solution, but we needed more than 45 mils of HCl to neutralize it. So if we needed more, that means our HCl was not as concentrated as our sodium hydroxide, and in fact that's what we get. We get a little bit lower than the concentration of sodium hydroxide. So our answer makes total sense. Let's look at the second problem. If it requires 67.0 mils of a 0.500 molar phosphoric acid solution to neutralize 15.0 mils of strontium hydroxide, what is the concentration of the strontium hydroxide? Okay, well, we start with the same formula as we have above, but now we're solving for the concentration of base. So we use this exact same formula, rearrange it, and get comfortable rearranging it. You'll notice all three acid items stay together. Those values are multiplied by each other, and then you divide by the two remaining base items to get your remaining base item in the calculation. And we know from the acid that the acid has 3 protons. So that's going to be 3 here. And we know our base has 2 hydroxys. So we know we're going to stick the number 2 there. And when we do that and we plug our numbers in, we end up with the following equation. Just make sure your volumes are in the right position. You're always going to be multiplying the similar things together on the same side of the dividing line of this fraction. That's one way to help you check to make sure you put in the right numbers in the right place. We divide it through, and you'll notice the milliliters again cancel each other, and the only unit left is molar. And there are no units for these because it's how many protons per acid or how many bases, how many hydroxides per base. So those have no units. And we end up with 3.35 molar strontium hydroxide, a very concentrated strontium hydroxide. In fact, so concentrated, I'm not quite sure if we can make something this strong. strontium hydroxide. It may not be quite so soluble, but that's the answer we get from this problem, and it's rounded to 3 sig figs because you'll notice the lowest number of sig figs is 3. In fact, all of our values have 3 sig figs in them, so our answer will also be with 3 sig figs. And our last problem on this page, how many milliliters of 0.275 molar sulfuric acid, okay, that has 2 protons, right, are needed to neutralize 25.3 mils of 0.154 molar sodium hydroxide. Well, that has 1 hydroxide group on it. So we set up our formula, and now we're going for the volume of the acid. So the volume of the acid is the 3 base values multiplied by each other divided by the 2 remaining acid values. So the setup is always easy. And now you're going to plug in the numbers. Well, we know that each base has 1 hydroxide, and we know that each acid has 2 protons, so we put those in. And then the rest is plugging in the numbers we already have. And you'll notice now we have two of these values that have molar in them, and the molar will cancel, so we don't have to worry about molar. Our remaining value is in mils. So if we wanted our answer in milliliters, we don't have to change our milliliters to liters. If we wanted it in liters, we could change it before we do the problem and leave it in liters, or we could do it after we figure out how many milliliters and then turn it into liters. It really doesn't matter. But in any case, we're going to get 7.08 milliliters of our sulfuric acid solution, and that's the answer to this problem. So let's look at a couple neutralizations. It takes 87 milliliters of a hydrochloric acid solution to neutralize 0.67 moles of barium hydroxide. What's the concentration of the hydrochloric acid solution? And remember, we don't have volume and concentration of barium hydroxide. We've already got calculated the number of moles. That's actually the volume times the concentration already worked out for us. So we're still going to use our original equation. It's just when we rearrange it, we're going to notice these 2 values, neither of which we have individually, but when you multiply them by each other, we have the actual value already calculated for us, the number of moles of the base. And now we just multiply it by how many hydroxides are on each base, which is 2. So we basically, instead of having 5 of the missing pieces, we have 3 of the missing pieces, and then 2 more combined into one piece. And therefore we have everything except our concentration of our acid that we're solving for. So this actually makes things easier, not harder in this case. And now we plug in our numbers, and you'll notice in this case you absolutely have to have your volume in liters. So it is very important you turn your 87 mils into 0.087 liters. Why? Because if you notice, your units have to be moles over liters in order to calculate 15.40 molar HCl, which will round to 15 molar HCl. Molar, remember, molar has to be moles per liter, which means our top value has to be in moles and our bottom value has to be in liters. So this is one of the few times where you really have to be careful about changing your units to liters. In all the other cases, it won't matter whether you keep it or you change it. You'll just get whatever unit is left. But in this case, you have no choice. The volume has to be turned into liters if you're calculating moles per liter or molar in this problem. Let's look at the last problem. It takes 58 milliliters of a sulfuric acid solution to neutralize 0.34 moles, okay, so again we have moles and we have milliliters, so you immediately should be thinking, oh, I need moles and liters instead. Okay, 0.34 moles of sodium hydroxide. What is the concentration of sodium hydroxide? Well, we use the same formula rearranged, and we also notice that we don't have the volume and the concentration of sodium hydroxide, but we have something better. We have the product of those 2 values, the number of moles already calculated. And we get this new equation. We know that each sodium hydroxide has 1 OH on it, so that number will be 1 here. And we know that each sulfuric acid formula has 2 acids in it, so that number will be in here. And the other 2 values we already have. We're going to plug those into our formula. And you'll notice we are already set up with moles over liters. Why? Because we already converted 58 mils to 0.058 liters. So again, when you see moles in the problem, you absolutely need to have liters for you to end up with a concentration in molar, molar being moles per liter. This is the one time where you really have to be careful. So if you see moles in the problem, in a neutralization or a titration problem, make sure your volumes are in liters for everything to work out properly. And when we multiply this through, we get 2.931 molar, because moles divided by liters is molar, which we round to 2 significant figures, in this case to 2.9 molar sulfuric acid. And that's the answer to this problem. And